So before we get started on any new material, does anyone have any questions from last week? All right, sounds good. So last week, let me just pull up my right PDF. Sorry, give me 1 second. All right, cool. So last week we talked about different ways we could compute probability. So we learned how to compute probability just by counting the number of kind of desired cases and of overall cases. And then we also talked a bit about how to compute probability when you can't just directly count how many cases there are. Maybe there's like an infinite number of cases and we could use geometry to count the probability. So for example, we can take the ratio of lengths or the ratio of areas or even the ratio of volumes. So this week we're going to take a look at yet another way we could compute probability, which is more using algebra when we're given some information about the relative probabilities that something happens, or the probability of something relative to the probability of something else, or we just like don't know directly the probability, but we need to solve for a probability as part of an algebra problem. And then in order to do this, we'll have to use some concepts from probability, such as concepts from probability, such as like when we multiply probabilities together, or when do we add probabilities together, and kind of learning about that. And then after we do this, we'll also cover a bit about conditional probability, which is basically how do we calculate probabilities when the probability is calculating on something given that we know something else has happened. So let's start with probability as algebra, and I have this all in a handout, so we'll do the same format, but basically we can start with a problem to illustrate. So if you look here at this middle part over here, you can take a look at this probability that it rains in this town, Birmingham, next Saturday is 1/3 the probability that it does not. We're given some sort of like relation for the probability, but we're not told directly what the probability is. And then the question says, what is the % chance of rain in Birmingham next Saturday? So before we go kind of to the solution, which I guess we thought about, or maybe you read a little bit about it. Does anyone here have any ideas on how we could approach this?
We can oh, go ahead. I was thinking we could use ratios.
Yeah. And keep going.
And find that and like use that to like add one. Like I don't know how to explain. I know the answer. I don't know how to explain how I got there.
Okay. You know? Okay. No worries.
Could I try?
Yeah.
We could find the ratio of it not raining to the ratio. Sorry, the ratio of it raining to the ratio of it not raining. So you know that the addition of them is equal to 1. So since it's not raining is 1/3 of it raining, then that ratio would be 1:3.
Yeah, awesome. So let me explain this, and it's in the notes too. So let's just get some variables. So maybe we say R is the probability that it rains next Saturday, and then N is the probability that it doesn't rain. So then we use ratios, or basically we want to write an equation to capture what we're told in the problem. So the first sentence says the probability it rains in Birmingham, so here it's R, right, is 1/3 the probability that it does not. So this is N. And from this, we can write the ratio R equals 1/3 N, or R over N equals 1/3 same thing. So we get this relation. And then the other thing that you said that was important was that because it either rains or it does not rain, these are mutually exclusive events, we know that the sum of the probabilities has to be 1. So we have r plus n equals 1. And we have 2 variables and 2 equations. So we basically have this system of equations over here. R equals 1/3 n, and then r plus n equals 1. So now we can just try to solve this. And remember, we're trying to find r because it says what is the % chance of rain in Birmingham next Saturday. So we might say substitute for n. So from the first equation, r equals 1/3 n. Let me use a darker color. From r equals 1/3 n, we can say n equals 3r. And then from r plus n equals 1, if we substitute n equals 3r here, then we can get r plus 3r equals 1. So 4r equals 1. So r equals 1/4. So then it's 25%. And if you go through the notes, that's also what we get here. Does anyone have any questions about this example? Cool. So the notes actually summarize a couple of really useful principles here. These are the ones at the bottom. So I want to spend some time going over this before we move on to more practice problems. So basically, just like with any other unknown quantity, you can use variables to represent probabilities. And if we use variables this way, then we can apply all the tools we know about algebra to probability problems, including all the methods that you already know in order to solve equations or systems of equations or inequalities. And then the other thing that we used here was if we have, this is more like specific to probability, if we have some probability that an event occurs, we can call it P, and then we can let maybe Q denote the probability that that event does not occur. We know that either P occurs or P does not occur. So we always know that P plus Q equals 1. And kind of in general, the sum of all possible probabilities must always equal 1. So this is often a fact that we want to use to get started with a problem, or maybe provide an extra equation when we're using algebra to solve these probability problems. So these are some, I guess, pretty important principles. So I also prepared a couple practice problems for us to do in addition to the one we just did, just to get a bit familiar with it. Any questions before we move on?
No, please.
Okay. So these are mostly from the worksheet. Can you all see?
No,
No.
the PDF sign is.
All right, what about that?
Yeah,
No.
it's not.
Okay, cool. So these are problems that are in the handout, and the handout also has solutions written down, but we'll go over some of it together. And then there's some extra problems in the handout that we're not going to go over together. So I'll kind of assign those as homework. So let's take a look at the first problem. So this one says, there's 3 times the number of orange fish as blue fish in a tank at the pet store, and there are no other fish. If Kaya randomly pulls out 1 fish from the tank, what is the probability that it is orange? So anyone have any thoughts on how we could get started with this one?
Well, first, we could start out with the simple fact that, let's say, probability of orange fish is O, probability of blue fish is B, O plus B equals 1. And we also know that O, the probability of O is 3 times the probability of B, due to there being 3 times the number. And that means that O equals 3B. So if we if we write the O plus B equals 1 equation again, we can replace O with 3B and add it to B to make it 4B. So that's going to be 1/25 for a blue fish, 1/4 for a blue fish, the probability of a blue fish. And if the probability of a blue fish is 1/4, then the leftover probability is 3/4.
Cool. So I'm just going to use A instead of O just because O looks a bit like 0. But basically what you said is we can get these two equations, A plus B equals 1, and then A equals 3B, right?
Yeah.
And then we want to solve for A. So we have, there's 3 times the number of orange fish as blue fish. So it's actually the opposite, right?
It should rather be 3. Yeah, it's 3. Oh, I wrote A equals 3B. Or is it?
Yeah, okay, that's right. So then there's 3 times the number of orange fish as blue fish. So there's 3, basically it's saying there's more orange fish than blue fish. And there's 3 times, 3 times the number of blue fish equals the number of orange fish. So A equals 3B. So then if we want to compute what A is, so what's the probability that is orange, we want to find what A is, then we can substitute here B equals 1/3 A. So then if we plug this into the initial equation, A plus B equals 1, then we get A plus 1/3 A equals 1. So 4/3 A equals 1. So A equals 3/4.
Well, there's a different way I would have done this. Since orange fish is 3 times blue fish, I just represented them as the smallest possible number. So orange fish could be 3 and blue fish would be 1. So since we know that 3 plus 4, sorry, the addition of the 2 should give you 1, and 3 plus 4, 1 plus 3 should give you 4. Then 3 out of 4 would be your answer.
Yeah, so here's another way you could do it. Let's say the number of orange fish equals like C, and in your case, since we're only caring about ratios, you could also say maybe C is 3. And then we know the number of blue fish is 1/3 of that. Or maybe we say it's like, D. And then we have the relation C equals 3D. And then the probability that we pick an orange fish, we may not actually have to solve any equation. We could say the probability that we pick an orange fish is the number of orange fish over the number of total fish, which is C plus D over, C over C plus D, which is 3D over 3D plus D, which is 3D over 4D, which is 3/4. That's another way you could do it too, is kind of computing the probability directly. Any other questions or thoughts on this one?
Could you also solve for the blue fish and use complementary counting to solve for the orange fish?
Yeah, you could. So if you wanted to do it the opposite way, you would get 1/4 for the probability that you pick a blue fish. And then you know that you either pick an orange fish or a blue fish. So then you'll get 1/4. I think in this case, it's a little bit more direct to directly solve for the number of orange fish, but either way will give you the same answer. Yeah. Cool. Let's move on to the next question. It's just another example of this. So we'll get into slightly harder problems. So this one is a different word problem. So we have two people, Dave and Eric. When Dave and Eric play chess, Eric is twice as likely to win as Dave is. And the probability that they draw, which means the game is a tie, is 1/10 the probability that Eric wins. So this is a two-part problem. The first one says find the probability that a game between Dave and Eric ends in a draw, and then also find the probability that Dave wins. So any thoughts on how to get started on this one?
Well, we could start by just writing down what we know. We know that probability of Eric winning is equal to twice as likely. Eric is twice as likely to win as Derek is. So we could say E equals 2D.
All right,
And
so
then-
first what's D? Oops.
Yeah,
sorry.
E is Eric, and since he's twice as likely to win as David, I wrote it down as E equals 2D. And then there's the draw option, which is 1/10 the chance that Eric would win. So we could say T, which is tie, equals 1/10 E.
All right, so let me just write down what you said. So P, Eric wins, we'll call that E. And then P, Dave and Eric draw, we'll call that a T. Sorry, can you say the equations again?
Yeah, so since Eric is twice as likely to win as Dave, we say that E equals 2D. And since the likelihood of them drawing is 1/10 the chance, the probability of Eric winning is 1/10 E.
Cool, so you said E equals 2D, and then probability that they draw is 1/10 the probability that Eric wins. So that was E equals, did you say E equals 10T?
1/10 T.
I see. So
Sorry, T equals 1/10 E.
yeah, T equals 1/10 E. Yeah, that's right. And then the last thing is we have three variables here, and we know that either Dave wins or Eric wins or there's a tie, and those are all the possibilities that can happen. So we also know that D plus E plus T equals 1. So now we have this system of equations here, and there's three variables and three equations, so we can solve for what we want here. So for part A, we want to find what T is, and for part B, we want to find what D is. So we can just directly solve the systems of equations. So one way we could do this, for example, is kind of substitute. So we could say, hey, E equals 10T, so 2D, E equals 2D, which equals 10T. So then D equals 5T. So if we substitute everything for T, which is what we want to find in part A, then we plug everything into D plus E, T equals 1. Then we get, and since D equals 5T, we have 5T plus 10T plus T equals 1. So this gives us 16T equals 1. So T equals 1 over 16. And then if we substitute that back in to D equals 5T, then we get D equals 5 over 16. So what that tells us is for part A, which is what's the probability that a game between Dave and Eric ends in a draw. That's going to be 1/16. And for part B, which is what's the probability that Dave wins, so what's D? That's going to be 5/16. Any questions on this one?
No.
All right, I have a couple more prepared just to get the hang of this concept on some harder ones. So here we have a different problem. So say we have this notation Pn, which represents the probability that an n is rolled on a die. A 6-face die with faces labeled 1 through 6. It's a weighted die, so that means that it's not necessarily true that it's equally likely to get any number. We have this like system of equations that shows us the probabilities of each of them relative to each other. So we know the probability of rolling a 1 is equal to the probability of rolling a 2. The probability of rolling a 3, 4, and 5 are all equal. Probability of rolling a 4 is equal to 3 times the probability of rolling a 2. And then the probability of rolling a 5 is equal to 2 times the probability of rolling a 6. So then it says if the die is rolled once, what is the probability that a 6 is rolled? So we basically want to solve for what P6 is. So any thoughts on how we could do this?
Well, first we could start by writing out the sum of the probabilities equal 1. And then we could try and substitute the different facts we're given to determine P.
Cool, yeah. So we know that we either roll a 1, 2, 3, 4, 5, or 6. So the sum of all of these must be 1, in addition to what we know above. Cool. So now we can try to substitute here, and we want to find the probability that a 6 is rolled. So maybe we can say let P of 6 equal X. And then let's see what we can derive from these equations up here. So this bottom equation, P of 5 equals 2 times P of 6, gives us P of 5 equals 2X, right? And then this up here gives us P of 3 equals 2X. P of 4 also equals 2X. And then this one gives us 2X equals 3 times P of 2. So therefore, P of 2 equals 2/3 X. And then finally, this top one, since P of 1 equals P2, that gives us P of 1 also equals 2/3 X. Any questions on any of that so far? Cool. So now we can plug into this equation. So we have P1 plus P2 plus P3 plus P4 plus P5 plus P6 equals 1. Now we've written everything in terms of X. So P1 equals 2/3 X, P2 equals 2/3 X, P3 equals 2X, P4 equals 2X, P5 equals 2X, and P6 equals X. So now we could sum this up. What we could do is maybe multiply both sides of the equation by 3. So we'll get 2X plus 2X plus 6X. And then this gives us 25. equals 3, which means x equals 3 over 25. So 3 over 25 is the probability that we'll roll a 6. Any questions or thoughts on this one? All right, I believe I have, okay, I have 3 more problems. And then we'll move on to the next topic. So this one's interesting. This one says, 2 people, Amy and Martin, and say they play a game in which they take turns flipping a fair coin until one of them flips a head. The first person to flip a head is a winner. If Amy goes first, find the probability that she wins. So anyone, any thoughts on this problem?
We can.
It's a 50-50 chance because it's a fair coin, which means you have an equally likely chance to get heads or tails. And it's 2 people, so they both have a chance of going heads or tails. So it is still equally likely among the 2 of them.
That's close, I think. But here the difference is that they're not flipping at the same time. So basically Amy will flip first, and then if she flips ahead, then she wins. If she doesn't flip ahead, then Martin goes next, and then he has to flip a coin. If he flips ahead, then he wins. But if he doesn't, then Amy gets another chance. So if you think about it like that, we can see that Amy actually has a greater than 1/2 chance of winning, because when she first flips, she has a 1/2 chance of winning on the first flip. But then if she flips tails and then Martin flips tails, then Amy has another chance to win.
Then we can take the total probability as a variable, for example, P, and we can say that the probability that Amy or Martin wins is half P. So we get P plus half P is equal to 1. Then we can add up and find the probability of Amy winning if she goes first.
Why is the probability that Amy wins half the or where did you get the fact that Martin wins half the probability that Amy wins?
Because if they all have 1 chance if any of them starts first, so if Amy goes first and she loses, she gives a 1 minus the probability of her winning to Martin.
Yes. I think I see what you're saying. So that's true. Maybe I'll explain a couple ways we could do this, and then you can let me know if what you were thinking was one of the ways. But I think like one way we could think about this that's like very maybe straight is we could think about we flip a sequence of coins, and maybe it's like we could get like heads, heads, tails, tails, heads, or we could get tails, tails, heads, tails, or tails. I'm just like randomly giving some examples. And so we want to find the probability that the first head occurs on some flip, like say the first flip or the second flip or the third flip. So the probability that the first head occurs on the first flip is going to be 1/2, right? Because we flip 1 coin. And then the probability that it's heads is 1/2. The probability that the first head occurs on the second flip, say first head occurs on flip. So the flip first, the probability that the first head occurs on flip number 1 is 1/2. The probability that it occurs on flip number 2 is going to be the probability that you first roll a tails, so that's 1/2, and then the probability that you then roll a heads, so that's 1/2. So that's 1/4, or 2 squared. What's the probability that the first head occurs on flip number 3? So that means we have tails, tails, heads.
1/8.
Yeah, so it's 1/8. And what about just in general, like n? So if the first head occurs on flip n, that means the first n minus 1 flips are all tails. What's the probability that that occurs?
1/2 raised to the power n.
Yeah, so it's 1/2 to the n. And so let's map this kind of problem back to this game that Amy and Martin are playing. So since Amy goes first, the probability that the probability that she wins, she will win if the first head occurs on an odd number flip. So if the first head is on flip 1 or flip 3 or flip 5 or 7, then Amy will win. On the other hand, Martin will win if basically the first head occurs on an even numbered flip. So if it's the second flip or the fourth flip or the sixth flip. Does everyone see why that is?
I'm a bit confused. So if we were to, so are we basically saying that since she's going first, there's a half chance that she will win, or are we saying, or are we just saying that if she goes on all the even turns, she might win. If he goes on all the odd turns, she might win.
So if Amy goes first and she flips a head, that's saying the first head occurs on flip number 1. And if that happens, then she wins. However, if she does not flip a head, then Martin gets a chance. And then if Martin flips a head, then Martin wins. So that's sort of the first head occurring on the second flip. However, if Martin also flips a tails, then Amy will flip again. And then if Amy flips a head, then she wins. So that's, if the first head occurs on flip number 3. If Amy still doesn't flip the head, then Martin flips again. And if Martin flips ahead, then he wins. So basically, each of them have multiple chances at winning if the previous person still hasn't flipped ahead. So if you think about like a coin being flipped until a head is flipped, then Amy will win if that first head is on flip number 1 or flip number 3 or 5, etc. Whereas Martin will win if that head is flipped on flip number 2 or 4 or 6, basically all the even number flips. Does that make sense?
Yeah, okay. Thank you.
Yeah. So now we could sum these together to get the total probability that Amy wins and the total probability that Martin wins. So the probability that Amy wins is the same as the probability that the first head occurs on flip number 1, plus the probability that the first head occurs on flip number 3, plus the probability that the first head occurs on flip number 5, and basically all the odd numbered flips. So it's actually an infinite series. Similarly, the probability that wins is equal to the probability that the first head lands on a even numbered flip. So that's you lands on flip 2 or flip 4 or flip 6 or flip 8 and so on. Any questions so far? All right, so now that we have this, we can actually evaluate this in a couple of ways. Did you all learn before the method to evaluate the sum of an infinite geometric series?
Yeah, we did it with Mr. Crawford.
Okay, awesome. So then you'll know that this is going to be 1/2. So you could write it at, say, 1/2, 1 plus. So this equals 1/2 times 1 minus 1/2 squared, because that's the ratio. So this is 1/2 times 1 over, this is 3/4. This is 1/2 times 4/3, which is 2/3. Another way we could do this, once we're at this step, is we can note that each term here is twice the term in Martin's series. So that will give us probability. It's a different color that's a little darker. So that tells us that probability that Amy wins equals 2 times the probability that Martin wins. Because if we times 2 over here, then we get 1/2. Then we get 1/2 plus 1/2, or 2 cubed plus 1/2 plus 1/2 to the 7th, which is exactly what is the value up here. So if we solve for this, we can say that probability of Amy wins equals 2 times probability that Martin wins, and then also probability Amy wins plus probability Martin wins equals 1. So if we say this is like A and this is B, then we have the system of equations A equals 2B and A plus B equals 1. And then if we want to solve for A, then we get A plus 1/2 A equals 1. So A equals 2/3. Any questions on this?
No, please.
All right, so I want to explain just one more way we could do this, which I think is really nice. So another way we could think about this is, let's say that the person whose turn it is to flip, maybe we can use the term they have control. So when Amy goes first, she first has control. So she's the one who's flipping. And so we could say like probability that person who flips, or maybe say person who has control wins equals, maybe we can call this P. And so Amy starts first, so she starts in control. And what happens when she flips? So the probability that she wins is, well, if she flips heads, then she will automatically win. So there's a 1/2 chance that she will flip a head and win. Also, there's a 1/2 probability that she flips a tails, and then she gives up control to Martin. When Amy flips tails and gives up control to Martin, so it's Martin's turn to flip, then Martin will then have a probability of winning of P, because now he has control. So the probability that Amy will win in the case that she flips a tail first is going to be the probability that Martin does not win. So that's going to be 1 minus basically P. Any questions on what I wrote down? I can try to explain a different way if that wasn't clear. Does that make sense to everyone?
Yeah.
All right. So then this gives us one equation where we could solve for P. So this we could solve a couple ways, but basically you can expand this out. P equals 1/2 plus 1/2 minus 1/2 P. So then this gives us 3/2 P equals 1, which gives us P equals 2/3. So these are three ways that we can solve this problem. Any questions or thoughts?
Could there be a case where Amy flips the coin once and gets ahead, and Martin doesn't get a chance to flip the coin?
Yeah, good question. Yeah, so that's captured in this term right here. So this is the probability that Amy rolls or flips ahead. And this is the probability. So this is Amy flips ahead. And then this over here is Amy flips the tail. And when Amy flips a tail, then the probability that she wins is basically the probability that Martin, who currently has control now, loses. So it's 1 minus P. Any other questions?
No, please.
All right, so I have another question. It's very similar. So this one says Amy and Martin, they play another game. Now they're rolling a die. And then they keep rolling until one of them rolls a 6. So now let's say Martin goes first. So what's the probability that Martin wins? So any thoughts on how we could do this one?
It'd be the same way we did the other one. Since it's a fair six-sided die, each of the numbers has 1/6 chance, and for the probability of them winning on each 10 is going to be 1/6. So if Martin goes first, and the probability of him winning on the first row will be 1/6. If he and then when he goes on the third one, it will be 1/6 to the third power. So it's just going to increase by 1/6, and then we just use that same geometric series that we had for the previous question, but it's 1/6 instead of 1/2.
Yeah, it's close. So yeah, again, we could actually do this in a bunch of different ways. So we can first do the geometric series approach, and then I'll show you also how we could do this without actually writing out the series. So we could view this as, Amy and Martin, they roll a sequence of die, and then until 6 is rolled. And so Martin wins if that roll is on like the first roll or the third roll or the fifth roll or whatever. And Amy wins if that roll is on the second roll, fourth roll, sixth roll, whatever. So we want to write down the probability that the first 6 occurs on roll, let's say n. So that means that we have, we first roll n minus 1 non-6s, and then we roll a 6. So what's that probability? What's the probability that we roll not a 6?
5 out of
Will it
6.
be?
Yeah, so it's 5 out of 6. And since we need to roll n minus 1 of n minus 1 non-sixes, that's going to be 5 out of 6. So that's n minus 1. And then we have to roll a 6. So we could write this as 5 to the n minus 1 over 6 to the n. So then the series we have is the probability that Martin wins equals basically the probability first 6 is roll number 1 plus probability first 6 is on roll number 3 or 5 or 7, etc. And so if we find the probabilities of this, the probability that the first 6 is on roll number 1 is just 1/6. Probability that the first 6 is on roll number 3 means we have to first roll 2 non-6s and then 1/6. So we know this is 5 squared over 6 cubed. Similarly, the probability that the first 6 is on roll 5 means we have to first roll 4 non-6s and then roll a 6. So that's 5 to the 4th over 6 to the 5th, and so on. And then similarly, probability Amy wins. That equals the probability that the first 6 is on roll number 2 plus the probability that the first 6 is on roll number 4 plus the probability that the first 6 is on roll number 6, and so on. So in the first example, that means we roll 1 non-6 and then 1/6. So that's 5 over 6 squared. In the second case, which is that the first 6 is on roll number 4, that means we roll 3 non-6s and then 1/6, and so on. So again, we can solve this in 2 ways. The first one is we could directly sum this geometric series. So we want to find the probability that Martin wins. So we could write this as 1/6 times 1 plus 5 squared over 6 squared plus 5/4 over 6/4, etc. So the ratio here is 5 squared over 6 squared. So this gives us 1/6 times 1 over 1 minus 5 squared over 6 squared. Sorry, it's a little small. All right, that's just how we sum a geometric series. So this gives us 1/6 times 36 over 11, right?
Yeah.
Which gives us 6 over 11. So that's one way we could sum this. Another way we could do this, I'll use a different color. Another way we could have done this is similar to the previous problem. We could have noticed that every term here is equal to, so every term here, if you multiply this term on the top row by 5/6, then we get this term on the bottom row. So what that means is 5/6 times the probability that Martin wins equals the probability that Amy wins. And if we call the probability that Martin wins, let's call this C and D, then we have 5/6 C equals D, and also C plus D equals 1. So remember, we want to solve for C. So we have 5/6 C plus 5/6 C equals 1. So 11/6 C equals 1. So C equals 6/11. So this is another way we can figure out the value. And then finally, I want to show the kind of analogy to the last approach we took on the previous problem, which is basically, we could also say that the person who's currently rolling sort of has control of the game. So I'll say probability that person who has control wins. We can just call this P. And Martin starts with control. So the probability that Martin wins equals, we basically want to consider two cases. So the first is Martin rolls a 6. And the second case does not roll a 6. So if Martin rolls a 6, he has a 1/6 chance of doing that, and then he'll win. If he doesn't roll a 6, then he has a 5/6 chance of rolling that, and then he sort of passes control to Amy. If he passes control to Amy, then Amy's probability of winning is just equal to P, which is probability she has control. So the probability he doesn't win is going to be 1 minus P. So basically this is saying that Martin can still win if he rolls not a 6 initially, and then Amy also doesn't win once she has control. And so we can then solve this system of this one equation. So this is basically saying P equals 1/6 plus 5/6, 1 minus P. So this says P equals 1 minus 5/6 P. So this gives us, if we move this to the other side, 11/6 P equals 1. So P equals 6/11.
Wendy,
Yeah.
I think there's a way to generalize this. I'm not too sure, but it seems like there's a formula.
Yeah, I mean, I think this is definitely generalizable if we have the same problem, right? So say there's some other thing that they're doing, like if Amy's rolling a 10-sided die, then you can generalize this to, this would be like 1/10 and then 9/10 in this formula. I would say the formula itself is not so important because it's maybe rare that you're going to see problems that are exactly of this form. But I think what's important here is that a couple concepts. One, that sometimes you might have probabilities that could be infinite sums if you are like playing some sort of game that goes on for an indefinite number of steps. I think the other key thing here is recognizing when the probability of something equals the probability of something else after something has happened. So in this case, the insight, I think, in the second approach is that when Martin does not roll a 6, then we kind of have the same situation all over again, right? Now Amy is going first, and we want to see if she rolls a 6. And so when we see that kind of same situation, then we can rewrite the probabilities in terms of the probability that Martin already wins.
I just wanted to point out that for both questions, let's say we make n the number of choices they have to roll. So your answer for the probability that the first person wins would be 2n minus 1. Sorry, n over 2n minus 1. Because in the first equation, they have two choices, heads or tails. That's how come you had 2 as your numerator. And 2 times 2 is 4, minus 1, that's 3. So 2 out of 3 was the answer.
And for this one, you had 6 out of 11, which is 12 minus 1.
Yeah, I think that makes sense. Yeah, I guess like my point there is like yeah, that's right. But I did want to emphasize that I think it's more likely that you'll see a problem where you'll kind of use these concepts than use the formula directly. If that makes sense. But you're right, that's how you would generalize this for sure. Any other comments or thoughts on this one?
No, please.
All right. Then I found one more, and then we'll end the algebra part with this one. So this one's another sort of die problem. So this one says, when rolling a certain unfair 6-sided die, and we have faces 1 through 6, the probability of obtaining face F is greater than 1/6. The probability of obtaining the face opposite is less than 1/6. The probability of obtaining any one of the other 4 faces is 1/6. And the sum of the numbers on opposite faces is 7. When 2 such dice are rolled, what is the probability of obtaining a sum of, the probability of obtaining a sum of 7 is 47 over 288. And then you want to find what is F. So what's the probability of obtaining this specific face F? Any thoughts on how we could do this one? All right.
Maybe we could start by just writing out the pairs of the numbers that form 7 and try to assign probabilities to these numbers, but like greater than or less than 1.
Yeah, so there's a couple of pieces of this. So we know that in this die, the sum of the numbers on opposite faces is 7. So there's usually 3 ways we could get 7. It's 1, 6, 2, 5, and 3, 4. And then we know that for some face F, it doesn't tell us which, but we could say like without loss of generality, maybe it's like face 1. Then the probability of rolling, let's say, let X equal the probability of rolling face F. Maybe we say without loss of generality that face is 1. So that means the probability of rolling the face. So we know that this is greater than 1/6. That means the probability of rolling any other face, like 2, 5, 3, or 4, those are all 1/6. So maybe we could write that the probability of rolling a 2 is 1/6. Probability of rolling a 5 is 1/6. Probability of rolling a 3 is 1/6. Probability of rolling a 4 is 1/6. And the probability of rolling a 1 is X. So what's the probability of rolling a 6?
2, 6 minus X.
Yeah, so that's 1/3 minus X. So I'll just write down what we said here. Without loss of generality, all right, so now we want to calculate the probability of obtaining a sum of 7. So probability, we get a sum of 7. There's 3 cases, right? So it's the probability that we roll a 1 and 6, plus the probability we roll a 2 and 5, plus the probability we roll a 3 and 4. So what's the probability that we roll a 2 and a 5? So the probability that we roll a 2 is 1/6, and the probability that we roll a 5 is 1/6.
So it's
So what's the
2/6.
probability? Sorry?
1 over 6 squared.
Yeah.
Oh,
Does everyone see that?
yep.
Yeah.
All right. And then what about the probability that we roll a 3 and a 4?
Same. 1 over
Still
6
one.
squared.
Yeah. And then what about the probability that we roll a 1 and a 6?
1/6.
1/3 x minus x squared.
Yeah, so it's x times 1/3 minus x. And then we know that the total probability of this is 47 over 288. Because that's what it says in the problem. Cool. So now we have an equation. So we have 47 over 288 equals, we can say 1/3 x minus x squared plus basically 2 over 36, which is 1 over 18. Any questions so far?
No, please.
All right, so now let's see how we could simplify this. So for example, we could multiply every side by, or maybe we could just combine the constants. So we can move everything to one equation, like move everything over here. That will give us x squared minus 1/3 x plus 47 over 288 minus 1 over 18. And if we factor, I'll do it over here, factor 288, we can see that, let's say that's 2 times 144, which is 12 times 12. So this equals 2 to the 5th times 3 squared, if I did that right. So this actually equals 18 times what are we multiplying by? 16? Did I do that right? Okay, so that means this is 47 over 288 minus 16 over 288. So then that's, that gives us 31 over 288. Did I do that right?
Yeah.
All right. I don't think this is quite what I want though. Let me check my math. Something here is not right.
Can we go on to shift the 31 over 208 to the other side? And since half of 1/3 is 1/6, we square 1/6 and add it to both the left-hand side and right-hand side.
Yeah, let me just check my math really quickly. I feel like maybe I have a mistake somewhere. Maybe you can help me check my math.
-47 minus 16, I think it's 21 rather.
Thanks.
No, that's 31.
Oh no, okay, yeah, it's 31.
All right, give me a sec. I'm just gonna check my notes because I don't want us to solve the wrong equation here. All right, let me restart my sharing. All right, so I think I did the math right, but I think we missed something here, up here. So the probability that we roll, sorry. So the probability that we roll 1 and a 6, we actually have to take into account both orderings. So we could roll a 1 and then a 6, or a 6 and then a 1. Similarly, for rolling a 2 and a 5, we could roll a 2 and then a 5, or a 5 and then a 2. And then for 3 and 4, we could roll a 3 and a 4, or a 4 and then a 3. So what we forgot here was actually to count for both of those cases. So 1/6 times 1/6 is probably roll a 2 and then a 5. But there's also a 1/6 times 1/6 probability that we roll a 5 and then a 2. So we should actually multiply all of these by 2. Does everyone see why that is?
Yeah.
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 All right. So let me just redo this to not confuse you all. So we can write this out. Similarly, same technique. So this will give us 2/3 x minus 2x squared. And then this will give us 2 over 36 plus 2 over 36. And then if we write this out, this will be 2/3 x minus 2x squared plus 1/9, just 4 over 36. So now we can also do the same thing, move this to the side. So this will give us 2x squared minus 2/3 x plus 47 over 288 minus 19 equals 0. So this gives us 2x squared minus 2/3 x plus 47 over 288 minus, so this is going to be 9 times 32. So 32 over 288 equals 0. Help me check my math. 2x squared minus 2/3 x. So now it's going to be 15 over 288 equals 0. That looks better. All right. So we can actually simplify 15 over 288. So it's divisible by 3. So this will give us 92,
6.
6, yeah, 96. Cool. So usually I like to get rid of fractions when I solve quadratic equations. So maybe we can multiply both sides by 96. So that's going to give us 192 x squared minus, I believe it's going to be 64x plus 5 equals 0. Did I do that right?
Yeah.
Yeah.
Yeah. All right. So how do we solve this equation for x?
Well, we could shift the 5 back to the other side and then complete the square of what's left.
Okay, we could do that. How do we do that?
So when we shift the 5, it becomes negative 5 equals to 492x squared minus 64x. Then we divide by 192 to get x squared minus 64 over 192 x equals minus 5 over 192. And
Okay.
after that, we then divide the 64 over 192 by 2 and the square, and we add the square to both sides of the equation. And then we compute, because of the half, we can then, because we know the half, we can then compute the square.
Okay. Is this right?
And it's the square root of that will give us 32 over 192 plus square root of 5 over 192 equals x minus 32 over 192. And then we shift the x minus 32 over 192 to the other side and then sum.
All right, so we completed the square here. So 32 over 192 squared. Right. Sorry, can you repeat what the next step was?
The next step was to find the square root of both sides of the equation and then make it so that it all equates to x.
All right, so let me just check my math here. Do we do the math correctly?
Isn't it supposed to be minus, I mean the last step, isn't it supposed to be minus 5 over 192?
Yeah, thanks.
Yeah.
Cool. So this will give us, so you don't want to do this math?
So the square root of that side of the equation is 32 over 192 plus or minus root of 5 over 192, which is equals x minus 32 over 192. And when you
Yeah,
shift
go
the
ahead.
32 to the other side, you get 64 over 192 plus or minus 5 root of 5 over 192.
Cool. So just to summarize, so I was doing some math here, but 32 squared over 192 squared minus 5 over 192 is going to give us 64 over 192 squared. You can check my math. And then if we square root both sides, then we get basically this equals 64, or sorry, I'll just square root here, 8 over 192, or negative x plus 32 over 192 equals 8 over 192, right? And then in this case, we get x equals 40 over 192. And in this case, we get x equals 24 over 192. All right, I think. So I think in this case, 192 is divisible by 8. So we get 5 over 24. And here we get 3 over 24. And then going back to our initial equation, so we want to find the probability of obtaining face F, and we know that it's greater than 1/6. So 3 over 24 is less than 1/6, but 5 over 24 is greater than 1/6. So that means we want to take this solution. One thing I'll mention here, oh yeah, go ahead.
For the last but 2 step, did you simplify the 32 squared?
Yeah. I did 32 squared minus 5 times 192.
Okay, thanks.
Yeah. So 32 squared is, so we could do this together, right? 32 squared is going to be 2 to the 10th, which is 1024. And then 5 times 192, I have to multiply this out, times 5, it would be 960. So then 1024 minus 960 should give us 64. And then I didn't multiply out the bottom because I knew that we wanted to take the square root. One other way to solve this, by the way, I just want to give an example, is you can actually factor this equation. Is this something that you learned with Matthew?
Pardon?
So, oh, did you learn how to factor quadratic equations?
Yes, like but very slightly.
All right, awesome. So another way we could do this without completing the square is we could figure out how to factor this equation. And what's helpful in factoring this is actually knowing how we could factor 192. So we could prime factorize 192. So we know 2 divides 192, and that will give us 96. And then again, 2 divides 92, that will give us 48. 48 is going to be 4 times 12. So this is 2 times 2. This is also 2 times 2 times 3, or 2 times 6, 2 times 3. So 192 equals 2 to the 6 times 3. And we could write out different factors. So it's like, 2 times 96, or 3 times 64, or 4 times 48, or 6 times 32, or 8 times 24, or 12 times 16. I think those are all the possibilities. And then over here, 5 is just 1 times 5. So we want to look for some way to write this 192x squared minus 64 plus 5. So in order to get, 64x plus 5. And in order to write this in some form, kind of like ax plus b, cx plus d, then we know b times d have to equal 5, and then a times c equals 192. And then also, if we cross multiply, so this equals ac x squared plus ad plus bc x plus bb, then ad plus bc has to equal negative 64. So we can kind of trial and error this, but basically we'll see that if we take, I think it's if we take 5 times 8 over here and 1 times 24, and we sum them, then we're going to get 64. So that means we can prime factorize this, or not prime factor, just factorize this polynomial as 24x minus 5 times 8x minus 1. And then we know this is 0. So then we can easily solve this by saying, well, this is 0 if 24x minus 5 equals 0, or 8x minus 1 equals 0. So then this one will give us the solution x equals 5 over 24, and this one will give us the solution x is 1/8. Same thing, we want to pick the solution greater than 1/6, so that's going to be this one. So it's just another way that we could solve the quadratic. Any questions or thoughts on this one? All right, I'm going to move on to a different topic then. But for the algebraic probability, there's a couple of other exercises in the handouts that I'd encourage you all to do, just to see more types of questions that use algebra to compute probabilities. And then there's also solutions included in the handout. So now we'll talk a little bit about independent and dependent probability before we move on to the concept of conditional probability. So I think we've mentioned this in some of the previous classes, but I want to just like make it more explicit. So under certain circumstances, we've been able to multiply the probabilities of 2 events together to determine the probability that both events occur. So for example, if we have the problem, find the probability that when 2 dice are rolled, the first die rolls a 3 and the second die rolls a 1. We could use a chart to compute the probability, right? For example, the first, we have them in columns and then the row to represent the second one. And the probability that that happens is just going to be 1 over 36 because we have 36 different possibilities and only one of them is the outcome that we want to calculate, which is the first die roll is a 3 and the second die roll is a 1. But actually, I think we already know that we could do this without building the whole chart. We could basically look at what's the probability that the first roll is a 3, and then what's the probability that the second roll is a 1, and we can actually multiply them together to get 1 over 36. So we have been doing this already, but basically the probability that the first roll is a 3 times the probability the second roll is a 1 is going to give us a probability, the total probability that the first roll is a 3 and the second roll is a 1. And this is just to illustrate this concept, which we've already been kind of using intuitively. When one result of one event does not affect the result of another event, then we call these to be independent events. And to compute the independent probability that both of these events occur together, we basically can just take the product of the probabilities that the event occurs. Any questions on this?
No.
Cool. So I want to contrast this with a different thing, so there's some examples here. But there's another concept called dependent probability. So in contrast with independent probability, when we're like rolling die, it's like each die roll does not affect the previous die roll. In some probability problems, circumstances might change over the course of multiple actions, and the final probability will depend on the changing circumstances. So let's look at this other example, which we will say is an example of dependent probability. So let's say an urn contains 12 marbles, exactly 5 of which are blue. This person, Yufei, draws 2 marbles from the urn without replacement. Find the probability that both the marbles he draws are blue. So we're finding the probability that there's 2 events that occur. The first event is the first marble is blue, and the second event is the second marble is blue, but it's after a blue marble has already been removed. So the second draw depends on the way that the first draw changed the number of marbles in the urn. And so maybe we could rewrite this problem to be a little bit more explicit. Find the probability that Yufei draws 2 marbles, given that he draws 1 marble from an urn where 5 of the 12 marbles are blue, and another marble from an urn in which 4 of the 11 marbles are blue. If we write it that way, then it's actually an independent probability problem, and we can multiply the probabilities together to solve it. Because initially he's drawing 2 things from the same urn, and once he draws one, that affects his second draw. If we reframe the problem as like there's one urn and then another urn, then those are independent sort of events. And then we can use multiplication, the principle that we learned above, to get the final probability. And then we call this an example of dependent probability. And so in particular, this like without replacement thing makes it so that it's dependent. If Yufei was drawing 2 marbles and he replaced it, then those would be independent events. And instead of doing sort of 5 12s times 4 11s, we would do 5 12s times 5 12s. So does everyone see the difference between why the dependent part kind of changes the probability calculation?
Yeah.
Yeah. So let's do an example just to make sure. I'll skip the independent probability ones. Let's try this one. So 5 students play a game of chance. Each one reaches into a bag and draws a marble without replacement. Only one of the 5 marbles is blue, and the student who draws that marble wins. If the students play the game 5 times, find the probability that each of them wins once. So thoughts on how to do this one?
Well, first we can look at the probability of the total wins that they can have.
Yeah, so let's first look at what's the probability that, so say 5 students play a game, this game, what's the probability that any of the students wins? Just one game.
There's is it 1/25th due to the fact that there's a 1/5 chance that a student will pick 1 out of 5 marbles, so 1/25th or 1/5 squared.
So if the students play one game, the probability that any student wins, so let's say the probability that student 1 wins is going to be 1/5. You can see this by saying, okay, maybe the first person draws the marble. They have a 1/5 chance of drawing the blue marble. And then the second student, they'll win if the first student does not draw a blue marble and the second student draws a blue marble. So this is going to be 1/5. The probability that the third student wins. So the third student is drawing after the first and the second student have already drawn. So they'll only win if the first student does not draw a blue marble and the second student does not draw a blue marble and the third student does draw a blue marble. So this is going to give us 1/5. And you can also see, using the same reasoning, probability student 4 wins is also 1/5. And the probability the last student wins is 1/5. So everyone has an equal chance of winning the game. So that's the first thing that I want to see. Now we want to see if the students play the game 5 times, what's the probability that each of them wins once? So the way that we could think about this is in the first game, it doesn't really matter who wins, any of them could win. In the second game, what's the probability that someone different wins from whoever won first?
4/5.
Yeah, so probability each person wins once. Okay. In the third game, what's the probability one different wins from the first 2 games?
3/5.
Yeah. And then what about the fourth game?
It's 2/5.
Yeah. And then finally, the probability for the last game that the only person who hasn't won wins is 1/5. So the answer to this is going to be 24 over 625.
But if the game is played 5 times, why isn't there also a 5 out of 5?
Yeah, you could do 5 out of 5.
Okay.
Yeah.
That's basically 1.
Yeah,
Yeah, I
it's
got
the
that
same.
question.
Yeah, so the 5 out of 5 is sort of saying, like, what's the probability that someone who has never won before wins? And in the first game, that's going to be 1 or 5 out of 5. And so this is another example of dependent probability, because the probability that we have sort of each subsequent student winning depends on what happened previously. And so that's why we have 5 times 4 times 3 times 2 in the numerator. And so going back to this handout, we did a couple of examples, but one to highlight, I guess it doesn't say here. Oh, here we go. Yeah, I want to highlight this. Very often the answer to a dependent probability problem in numerator with a factorial expression, because it involves counting permutations. So we saw, for example, up here, in this example, we did 5 times 4. In the example we just did, we got 5 times 4 times 3 times 2 times 1. So oftentimes it's dependent because we're doing a permutation rather than kind of doing the same thing over and over again, where we're more likely to see an exponent in the numerator. So there's a couple of other example problems here that I'll leave as homework problems as well. But I wanted to take this idea of independent and dependent probability and talk about basically conditional probability. So I think one of the best ways to explain conditional probability is to look at an example as well. So for here, let's look at this example problem. So this one says, Russell rolls a pair of dice with his eyes closed. His sister tells him that the sum of the dice is greater than or equal to 9. Knowing this information, Russell calculates the probability that he rolls doubles. And then what is that probability? And so if I had a different problem, that's just Russell rolls a pair of dice, what's the probability that he rolls doubles? What would you guys say?
Well, it'd be all the sums that are greater than 5, greater than 9 or equal to 9. And then we'd also find the total number of combinations we can have, which we already know is 36.
So let's forget for a sec this problem. Let's say we have a different problem. Russell just rolls 2 dice. What's the probability that he rolls doubles? How would you do that one?
It will be 6 out of 36, which is 1/6. Because he can either have 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, or 6, 6.
Yeah, that's right. So basically there's 36 different possibilities for the rolls. He could roll 1, 1, then 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, or 1, 2, 2, etc. And then out of those, 6 of them are doubles. So the probability is 1/6. All right, so now let's look at this one. So again, we could write out all the different possibilities, but now we know this information that the sum of the dice is greater than or equal to 9. So if we look at all these possibilities, instead of all of them being possible, only the bolded ones, so I'll kind of underline them, only these bolded ones have sum greater than or equal to 9. And there's 10 such outcomes. So because we know this information, this condition, we actually use that as our denominator instead of all 36 possibilities. Similarly, out of all these 10 rolls, only 2 of them are doubles. So that's going to be this and this. Any other doubles does not sum to 9 or greater. So in our numerator, we're actually only going to have 2 as well. So given that the sum of the dice is greater than or equal to 9, the probability that Russell rolls doubles is going to be 2 out of 10, or 1/5. So this is an example of what we call conditional probability. We have over here, this is the condition. And so that changes the probability that we're calculating. If we didn't have this condition, we would get 1/6. But since we know that it's equal to 9, then we only consider the possibilities in that universe. And in this case, we'll get 1/5. Any questions or thoughts on this problem?
So the condition was that we had to do use sums that were equal to or greater than 9, which helped to simplify the problem instead of using all the data given.
Yeah. I mean, I guess in some cases it simplifies the problem, in some cases it makes it more complicated. So before we do a couple of example problems too, I wanted to show also this formula. So basically, I'm taking a look at this paragraph over here. So for conditional probability, the conditions under which an event occurs can change the kind of dramatically under different conditions. So if we have some event A, so for example, in this example below, it's going to be like rolling doubles. And then C is the condition. So for example, it's that the sum is greater than or equal to 9. Then the probability that an event happens given a condition, we use this notation PA, and then we draw a bar C, which is basically saying the probability that A happens given C happens. And then the way that we computed this is we take a look at the probability that both events happen. So what's the probability that A happens and C happens? And we divide that over the probability that C happens. So for example, in our rolling a dice example, I'll go back here. The probability that we get doubles given that the sum is greater than or equal to 9. This equals the probability that we get doubles and the sum is greater than or equal to 9 over the probability that the sum is greater than or equal to 9. And the probability that we get doubles and the sum is greater than or equal to 9 is going to be 2 out of 36. And the probability that the sum is greater than or equal to 9 is 10 over 36. So it's going to be 2 over 36, or sorry, 2 over 10, which is 1/5. And so this is a formula that's actually super useful for conditional probability. And then oftentimes we can take a shortcut by kind of canceling out the denominators, if you will. So in this case, you know, we didn't actually have to calculate over 36. We could just basically say, what are the outcomes in which this condition is true? And what are the outcomes in which the condition and the event we're looking at can happen, and divide them. So sometimes you might want to go back to the formula. Sometimes you could count it directly, but ultimately they'll give you the same answer. Any questions so far?
No, please.
All right, so let's do a couple of examples. So here's one. We have a fair coin. We flip it 4 times. Given that exactly 3 of the flips are heads, find the probability that the first flip is a head. So how might you all do this one? Any thoughts?
Well, first you can start by finding out the total number of four flips of the coin that have 3 heads. So that would be 4 choose 3, so 4. And then how many have heads starting? So
Cool. So I'm just writing out, you said first flip is a head is the probability that, the probability that the first flip is a head. I should write this more precisely. Given that 3 flips are heads equals, so the numerator is going to be number of sequences with first flip as a head and 3 flips are heads over number of sequences where 3 flips are heads. So if we could write out, for example, the number of sequences where 3 flips are heads. So that's just going to be tail, heads, 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 tails, heads, 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 tails, heads, 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 tails. Right. And so out of these sequences, we see that 3 of them start with heads. So this is going to be 3 over 4. Any questions or thoughts on this one?
no, please.
All right, we'll do a slightly harder one. A similar idea. Mary randomly chooses an integer from the integers 1 through 100 inclusive. If Mary chooses a multiple of 4, what is the probability that she chooses a perfect square? So how do we do this one? So we want to compute probability that she chooses a perfect square. Given that she chooses a multiple of 4. Any thoughts?
So the denominator would be the total number of multiples of 4 from 1 to 100 inclusive. So we just divide 100 by 4, which is 25.
Okay. What about the numerator? So the numerator, we want the number of perfect squares that are also multiples of 4.
There are 3 perfect squares that are multiple of 4.
I think it's 5.
Yeah, so there's going to be 4, which is 2 squared. Then there's going to be 36, which is 6 squared. And there's going to be, oh, well, we could do this in order. 16 is 6 squared. 16 is 4 squared. 36 is 6 squared. 64 is 8 squared, and then 100 is 5 squared. Sorry, 10 squared. And another way you could do this is sort of 2 times 1 squared, 2 times 2 squared, 2 times 3 squared, 2 times 4 squared, 2 times 5 squared. So it's going to be 5 over 25. So the answer is 1/5. Awesome. All right, any questions on this one?
No,
All right. I'm going to skip this one and we'll do this one. Sorry, I forgot to do a page break here, but let me see if I can. Maybe I can just cover this temporarily so we, okay. Let's just read the first problem. So let's ignore the second problem for now. So Mandeville has one standard quarter and one special quarter with heads on both sides. He selects one of these two coins at random, and without looking at it first, he flips the coin 3 times. If he flips a head 3 straight times, what's the probability that he selected the special quarter? So this one's a bit more complicated, but we want to calculate the probability he selected the special quarter. Given that he flips 3 heads. So this was an example where we can't directly just count one over the other. So here we actually want to use our conditional probability formula. So remember, this equals a probability that he selected the special quarter and flip 3 heads over. So this is, if we call this event A and this condition C, then this is probability A and C over the probability he flips 3 heads. So this is probability of C. Does that make sense so far?
Yeah.
All right, so let's start with maybe the numerator. So what's the probability he selects? I'll just write. He selects the special quarter and flips 3 heads.
The probability that he selected the special quarter and flipped 3 heads is 1/16, I think, because he has 2 quarters, and so it's a 50-50 chance that he chooses one of them from his pocket. And the probability of getting 3 heads in a row is on a regular standard quarter, that is 1 out of 8. So yeah, it's 1 out of 8. So it's 1/2 times 1 out of 8, which is 1/16.
So you're close. So it's 1/2 probability that he selects the special quarter, but then the special quarter has heads on both sides. So that means if he selects the special quarter, then he's gonna flip 3 heads with probability 1. So the probability that he selected the special quarter and flips 3 heads with that special quarter is just 1/2.
I'm going to use
make
the
sense?
probability for the other quarter. I should have used the one.
Oh, yeah. So now let's do the probability that he flips 3 heads overall. So how do we calculate this?
Well, it would be the probability that it's 3 heads with the standard quarter multiplied by the probability it's 3 heads with the rigged quarter, right? So 1/8 times 1 is still 1/8. So probability that he flipped 3 heads in a row is 1/8.
That's close. So we actually need to multiply that with the probability that he selects each quarter. So the probability that he flips 3 heads, we could do this using casework. So there's sort of case 1 where he selects the special quarter. And case 2 is he selects the regular quarter. If he selects the special quarter, then the probability that he gets 3 heads is 1. If he selects the regular quarter, then as you said, the probability that he gets 3 heads is 1/2 times 1/2 times 1/2 is 1/8, right? Now the probability that he selects the special quarter is 1/2, and the probability that he selects the regular quarter is 1/2. So the total probability that he flips 3 heads is going to be the probability that he selects special quarter and flips 3 heads plus the probability he selects regular quarter and flips 3 heads. And that's going to be using sort of independent probability here. Probability he selects the special quarter times the probability he flips 3 heads with the special quarter. Plus, so that's, I'm just rewriting this quantity here, plus the probability he selects regular quarter times the probability he flips 3 heads with the regular quarter. So the probability he selects the special quarter is 1/2. The probability he flips 3 heads with the special quarter is 1, because they're all heads. The probability that he selects the regular quarter is 1/2, and the probability that he flips 3 heads with the regular quarter is 1/8. So this gives us 1/2 plus 1/16, which gives us 9/16. Any questions on that so far?
And please, I don't really get why the probability for the case if he selects a special quarter is 1, because the total probability should sum up to 1. So if that is 1, then
Yeah, so basically the special quarter has heads on both sides. So if he gets the special quarter, that means he'll always flip heads. So when he flips 3 times with the special quarter, the only sequence that he can get is heads, heads, heads. So the probability that he gets, heads, tails, tails, or heads, heads, tails, or all the other sequences is 0. So the sum is still going to be 1. So when you flip three coins, you can get heads, 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 tails. I'll write down all 8 possibilities. These are all the possibilities you can get when you flip 3 coins, right? So,
Yes.
so if we use the special quarter, let me use this color, then the probability that I get 3 heads is 1 because I can only flip heads. And then there's no way for me to flip tails. So the probability that I get any of these others is 0. So it still sums to 1. In the other case, I'll use a different color like green. If I select the regular quarter, then the probability I get heads, heads, heads is 1/8. The probability that I get any of these other sequences is also 1/8. So the sum is also 1.
Okay, thanks.
Yeah, no problem. So let me just finish this up really quickly. So now we've computed the probability that he selects the special quarter and flip 3 heads, which is 1/2 over here. And then we've also computed the probability overall that he flips 3 heads, which is 9/16. So we can plug it back into this formula up here. So that gives us 1/2 over 9/16. So that gives us 1/2 times 16 over 9, which is 8/9. So that's the solution to this first problem. Any questions on this?
No, please.
All right. So I highly encourage you to go back to the handout and go through some of these other conditional probability problems. There's 3 more, or we did one of them. There's 2 more, just to get familiar with the idea of conditional probability. And then I will see you all in office hours on Friday. And if you have any questions on any of this, again, feel free to post in Piazza. Thanks so much for coming.
Thank you, Miss Wendy. See you on
Thank you.
Friday.
All right, bye.
Okay, thank you. Bye.
Hey, Wendy.